Okay, this is lecture 10, and today we will talk about very important relation or expression, so-called Pao-Sa double integral. So Pao, this is a family name of a researcher, and also Sa is also another family name of two researchers. So they have published a very important work previously, several decades ago, and we will just revisit that topic in today's lecture. Okay. So before talking about our today's lecture, we wanted to talk about the state of the art. So how does the state of the art device looks like? This is a very schematic diagram of our state of the art device. So there you can see some gray regions. So this one, gray regions, and also another one, purple regions. So here gray is corresponding to silicon, and here we have a purple, and that is corresponding contacts. So here we can find three different pieces of purple regions, and as you can easily imagine, one of them is working as a source, and the other one, the symmetric one, is working as drain. So whether which one is a source and which one is drain, that doesn't matter. So at least in their structure, their intrinsic structure, they are identical and symmetric. So one of them is a source and one of them is drain. And here you can see there is another one which covers several silicon pieces. So how many silicon pieces you can find? There is 1, 2, and 3 silicon pieces, and these silicon pieces are just surrounded by this metal line. Although it is just shown as a surface like one, but we have to understand actually this seemingly void is filled with metal. So this purple surface just shows the surface of a certain region. So we have all metal material filling all over this structure. So if we can make the cut of our entire structure along this line, then maybe we will find that this structure just looks like small silicons, small silicons corresponding to 1, 2, 3, and 1, 2, 3, and all other parts are just filled with this metal. Of course, in order to separate this silicon and metal, we have to introduce certain insulating layer, and insulating layer is not shown in this part. So that is the general structure of the state-of-the-art device transistor, and it is currently called as multi-stacked nanosheet field effect transistor. Why do we have this kind of long name? So stack means that here we have 1, 2, 3. Each silicon piece is called as a stack, and there are 3 stacks, not single stacks. There are multiple stacks, so that's the reason why we call it as multi-stacked, and each stack is called as also nanosheet. Nano means that this is the size is small. Yes, we understand this. They are nanometer scaled, and sheet means that when we first introduced this technology, so the cross section was not ideally like this. So this one, it's a cross section. So here we have, for example, roughly 5 nanometer, and its width is, if that is the smallest, then it is corresponding to 10, and even we can have a much wider one, 20, 30, 40. So if we draw in that way, then you can find that this is like a sheet, like structure. This is a very narrow, thin, and wide. This is thin and wide. So in this case, we call it as a sheet. However, if we reduce the width of this structure, then let's just say that if we go to almost 1-to-1 ratio between thickness and width, then please, once again, try to describe each shape. Can you say this is thin and wide? In this case, actually you cannot. It's just like isotropic. Even this vertical direction and lateral direction, we have similar size. So in this case, it is called as not nanosheet but nano wire. So at the beginning of our technology development, people thought that, oh, the best structure for our next technology may be nanowire, because nanowire has a symmetric structure along this lateral direction and vertical direction, so they thought that that would be the best way. But about 10 years ago or 12 years ago, researchers found that actually that from the viewpoint of current or charge collection, nanosheet is the best one, but in real fabrication, nanosheet or nanowire is not that much ideal. In order to maximize the current density for our structure, actually we have to adopt this nanosheet technology. That was the conclusion by IBM researchers and other researchers. So that's the reason why at the time, once that paper was published, then people thought that, okay, we have stopped developing nanowire and moved to the nanosheet, and that's the reason why currently we have a nanosheet technology. So I think that at least for in the future 10 years or about 20 years, we will live with this structure. But later, what will happen? It is not that certain. So this is the state of the art. So let's go to today's lecture contents. But although we are working or living in the era of this multi-stacked nanosheet field effect transistor, but today's lecture starts from this planar MOSFET. So planar MOSFET, the last one was around 20 something nanometer technology was the last generation of planar technology, and we are now living in the era of 3 nanometer and 2 nanometer, and maybe you have heard about Intel's the latest technology, 1.8 nanometer technology in risk production a few days ago announced. And between them, we have several generation gaps. So if we allow certain year gap, then this is more than a decade difference exists between this planar technology and current FinFET or nanosheet technology. However, still, we have to start from this planar one because that is the basic of our modeling and theory and understanding. After that, we can move to more advanced modeling technique. Okay, so we will start from this planar one. And please note that although the state-of-the-art devices are fabricated with FinFET technology and nanosheet technology, but still there are tons of transistors actually fabricated in the planar architecture. So once you have a new technology, then suddenly all old technology disappears. That is not the actual situation. Only, so let's say that this is the progress of our technology. For example, here we have a planar technology, and here we have a FinFET technology, and now we have a nanosheet, and later we will have an even further advanced one. So once we are currently living in this nanowire, nanosheet technology. So maybe some of you say that, oh, there is no longer planar MOSFET being fabricated. Actually, the situation is completely different. There are tons of devices are being actually fabricated even today. But problem is, once you fabricate this one, that does not make much margin to or financial benefit to you. So because it becomes extremely cheap, so therefore in order to survive in this planar technology scene, then your company, your fabrication should be really efficient, and with such a small margin you can win the competition. So still, most of financial benefit comes from this state-of-the-art devices, because Nvidia and Apple and all kinds of big tech companies are fabricating the fastest one, the most powerful one, using this nanosheet technology or FinFET technology and getting a lot of money. But there are many other ones. For example, if we turn it on and turning off the light, so can we use FinFET or nanosheet technology? Actually, that doesn't make sense. So still, there are a lot of planar MOSFET available. And another one is especially important for this one. If we go to some specialty technology, specialty applications, even FinFET or nanosheet technology suffer from certain technical difficulties. For example, let's consider RF, radio frequency. So in this case, maybe we can say this way: well, FinFET is much more advanced than planar MOSFET, so its RF performance would be always superior than planar MOSFET. But the reality is not that so. So the clear benefit of performance shown in FinFET or other kind of one is dominant in its digital application. So when you try to make a digital circuit, digital system, certainly the state-of-the-art device shows much benefit than the previous ones. However, in terms of RF, this is the combination of also digital and analog scene. So if analog part is related, then that is also related with a certain capacitance inside this system. Parasitic capacitances are all very important. In the case, there is no guarantee that state-of-the-art technology shows much better performance than previous ones. So that's the reason why if you are working as an engineer in a company, and if you are just assigned to non-digital, non-state-of-the-art devices, maybe you can find other technologies seemingly outdated, but they are still being used actively for certain applications. So don't try to say, okay, so only the state-of-the-art one is the best one. And yes, anyway, so we started from this planar MOSFET. So let's go to this structure. So here we have a three-dimensional structure: X, Y, and Z, and this Z direction is assigned to most insignificant direction. So this is width direction. So we will just consider everything is just homogeneous along Z direction. So now we have vertical direction. This is X direction, and channel direction is Y direction. So depending on the literature, sometimes people say that X is channel direction and Y is vertical direction, and sometimes people say in this way. I think that yes, so there is no well-defined or universal agreement for coordinate system, because when we talk about just one-dimensional system, vertical system, this is quite natural to say this is x. But if we concentrate on the transport, then it is quite natural to say that the channel direction is x. So what is your starting point? That determines whether you set x as a vertical direction or channel direction. But in this book, Professor Tao's book, he starts from vertical structure, one-dimensional structure, and expanding it to the three-dimensional structure. So it is quite natural to say that this is vertical, x is vertical, and y is assigned to the channel direction. So although I write down in this way, so please try to fill the missing part. So if I have to draw the entire structure, the MOS structure in the at least in its planar structure, how can you fill out the missing part? So where can you find the substrate? Of course, our substrate is substrate content is exists here, and this is a substrate, or sometimes called as body, and the distance between this interface and substrate is regarded as infinitely large. So that is one thing. And another contact, gate contact. Where can you find the gate contact? Actually, here we can find the gate contact. This is gate contact. So if we have to specify the location of a gate contact, then we have to say in this way, oh, gate contact is located at a plane at x equal to minus T ox. If we say T ox is the thickness of oxide layer, then that will be the position of a gate. And where can you find source contact and drain contact? Oh, now that is the real question. So in this case, we say that here we have source. Conventionally, we say that x equal y equal to 0 is close to the source contact, and say that y equal to L, the channel length L, that is close to the drain contact. That is the usual assumption. So actually, usually we draw only central part, but in reality, the shape of our the smallest device is not like this. So this is a more realistic view for our transistor. So when we scale down our channel length as much as possible, then usually the channel length and source length and drain length, these lengths are really comparable. So we have considerably long source, considerably long drain, and also similar lengths of a gate. This is the real situation for the shortest device. But right now, we are considering a long channel device. Here, long channel means that compared with this channel length L, our source length and drain length can be regarded as quite short. Okay, so now that is of course under the assumption that source and drain are maintained as their shortest length scale. So now we have this kind of structure. So you understand our drawing just completely neglect two parts. Source is neglected and drain is neglected. What we are considering right now is just the intrinsic part underneath the gate oxide. Then what is the condition and what is condition at these two boundaries? That is actually very important question, which is not usually discussed in textbook. So actually, when we really try to model this entire system, including source and drain, this part makes a lot of problems. So, but right now we do quite a simple approach. Yes, source is so highly doped as N plus. So like 10 to the 20 per cubic centimeter, 10 to the 21 per cubic centimeter. So here we have a really high conductivity. So there is no voltage drop between the external contact. So here we have, so usually what we have in reality is we have a certain metal line or metal pillar called as via, and this via is connected to our source part. So please let me just draw once again. There is a box called as source or drain. This is a highly doped silicon box, and on top of it we have another metal pillar attached to this system. Yes, here we call it as a via, and of course we have another metal line, horizontally running. So if we apply, for example, 1 volt, then this 1 volt is just to propagate in this way and eventually propagate to that way, because metal is regarded as a very good conductor, and also even this source and drain is so highly doped and they have quite a high conductivity. So that's the reason why in this modeling we will say that the quasi-Fermi potential at this source side is just given as source voltage. And here we have another the opposite end attached to the drain, and we will say this quasi-Fermi potential at that point, the drain end, is regarded as simply drain voltage. Means that if you apply 1.0 volt to your drain, then actually the quasi-Fermi potential at this point is also set to be 1.0 volt. There is no voltage drop between your external drain and your internal drain. So that is the first assumption. Of course, when you go to the realistic device, then we have to consider finite resistance between this internal drain and external drain. And if we consider this drain, then there will be certain voltage drop. So although you apply 1.0 volt, but actual voltage applied to your channel can be lower than that. So are you with me? Quite similarly, although we can apply 0 volt to our source, but internal source voltage can be differed from that grounded voltage if there exists a certain source resistance. So please understand this one. But anyway, we will live with this kind of a simplification. Well, the one, yes, uniform p-type substrate is assumed. So maybe you can say that, well, p-type substrate is not exactly uniform. In many cases, we introduce intentionally certain non-uniform doping profile into it, usually to control the subthreshold voltage. But for a while, just to assume there is a uniform p-type substrate. And you know that the only important one for our purpose is not the variation of doping profile in deep substrate. That doesn't make any sense. The only important doping profile to us is nearby, just nearby depletion region. and inside the depletion region. So here we only need something around just orders of not exactly 10, but orders of 10, several 10 nanometer. That kind of length scale is important for us to determine the the threshold of our transistor. So we will use this uniform p-type substrate. Okay, so maybe you can think that is this enough, or is this enough to describe our complicated device structure? So when you come back to the realistic structure and our simplified view, you can find that there are a lot of differences. So for example, entire this parasitic source and parasitic drain parts are just gone away. We are now just concentrating on this central channel part, and we will say that this is the core of our transistor. And the fact is, yes, it is the core intrinsic device. So by modeling this core part properly, we after that adding some additional consideration for parasitic components, we can describe our transistor quite well. Okay, so please, we can go with this kind of approach. And we must start from this gradual channel approximation. Interestingly enough, Professor Tower visited Korea in this year, February, in a conference. And although I missed that presentation, I also heard that actually he proposed that he have invented a way to beyond this gradual channel approximation, and he promised to the audience that he will make his first version book, and in his first version book he will add this beyond gradual channel approximation contents in the textbook. But you know that will take some time, so right now we will live with this gradual channel approximation. But anyway, gradual channel approximation is really important for our discussion. What is the gradual channel approximation? Here, the meaning of a gradual channel, here we have y equal to 0 and y equal to L. This is drain end and this is source end. And when you say gradual, means that along this y direction, the electric field is not that much strong. That is the meaning of a gradual. Electric field or potential changes gradually along channel direction. That's the reason why we say the gradual channel. So it is nothing related with its geometry, but its potential profile is changing gradually along the channel direction. So if we assume that potential is gradually changing, then by taking its first order derivative along this channel direction, this is corresponding to the y directional or channel directional electric field. So if we say that potential is gradually changing, simply speaking, this is quite small number. Okay, so simply speaking, we say that channel directional electric field is small. But small means that we need a certain criterion. So when we make it, this is a small and this is a large, compared to what? So in this case, we say that this way, along vertical direction, along vertical, the component along the vertical direction, we have relatively small differences in our lateral electric field. So I just told you in terms of electric field, but more more exactly, this is the exact description about gradual channel approximation. Here we are now talking about the once again second derivative of electrostatic potential along x direction and y direction. It means that Ex and its x directional change, and Ey and its y directional change, and this one shows that this x directional change, vertical change, is much higher than lateral change. So why do we introduce this kind of seemingly strange approximation? Then please have a look at our Poisson equation. Previously, we just thought about one-dimensional Poisson equation, but now we have to consider two-dimensional Poisson equation. Why? Because we are now considering an x and y plane. More generally, we have to consider x, y, g space. So in this x, y, g space, what we have to do is actually this one. Second derivative along x direction, y direction, and also we have to consider second derivative with respect to z direction. But why we don't have this third term? Third term can be neglected quite safely because we have assumed that every quantity is just homogeneous along z direction, so we don't have to worry about this quantity. It's okay. But remaining one, yes, now we have two terms. Well, we have already done quite impressive job with only this x directional Poisson equation, but now we have a very annoying term corresponding to the second derivative with respect to the y direction. So what we did with the gradual channel approximation is, simply speaking, although we must consider this second term, well, it's not important. I will neglect it. So just to neglect it. This procedure is called as gradual channel approximation. Then how can we justify ourselves? So in this case, okay. So if once we have the general solution, the numerical solution of our system, then we can justify, actually, when you compare, make a comparison between these two terms. Yes, this one is dominant. Yes, we can do it, but more intuitively think about this one. We are now considering very long channel device. It is very long, and here and there they are much separated, and we have applied very small drain voltage which is quite close to zero. For example, 1 millivolt, 10 millivolt, 50 millivolt. So, but in vertical structure, we apply, for example, 1 volt, 2 volt, 3 volt to our structure at gate contact, and that is just separated by very short length scale, just Tox. Tox is orders of nanometer scale, and length is orders of at least 100 nanometer or several micrometer in our case. So what you can expect is, in this structure, maybe we have a strong electric field in vertical and relatively small electric field along y direction, channel direction. So since electric field itself is quite large, so its variation would be also high along x direction. And since electric field itself is so small, its variation, position-wise variation, can be also quite small. That is our rough justification about neglecting this one. However, please note that from the viewpoint of this Poisson equation, the great motivation for adopting this gradual channel approximation is, by adopting this gradual channel approximation. Now our two-dimensional partial differential equation x and y can be simply written as an ordinary differential equation with respect to x. Now this y, the channel position, can be used as a simply a parameter. When a given position, we can just consider vertical structure. Once we consider this vertical structure, then every analysis becomes exactly identical with that of a MOS system. So although we have to consider 2D, but what we did is, yes, actually we have to consider the entire system, but instead of that, I will just solve several pieces of this one-dimensional system. How can you justify this one? Because their interaction is not that high, so we can just consider all over this one, these slabs. That is the way we do. Okay. Then natural question is, okay, that is your argument. Then can we really satisfy this condition, the assumption? Fortunately, in many cases, wow, that is really true. So we can use this gradual channel approximation in many cases. Where can you have a certain breakdown or failure of this gradual channel approximation is when we apply too high drain voltage. Then now in this case we have quite a strong lateral electric field, and this high lateral electric field also introduce high variation of our lateral electric field, so that will make some disobey of this gradual channel approximation. So that is the one we have to be careful. But anyway, this is quite strong. Except for that condition, we can apply this gradual channel approximation quite well. I think that this is one important understanding. Once we understand this gradual channel approximation, then the next thing is quite straightforward. Why? The equation structure is exactly the same with our previous MOS structure. So here we have a hole, and here we have electron, and here we have doping density, but this is a constant. Okay, good. Now what we did was hole density and electron density were expressed in terms of potential. So do you remember at the time, if we adopt Professor Tower's notation for our electrostatic potential, then it was related like this. If we have this one, exponential minus phi over kBT over Q. That was the expression, and also that was very small number and exponential plus phi over kBT over Q. Please note that there is a positive and negative sign. That was our previous assumption used in our MOS system. But when you have a look at this expression, we must understand this one. Electron density, please just review what we did. Electron density is actually written as, if I adopt phi in our conventional notation, not Professor Tower's notation, then electron density is given as intrinsic carrier density, exponential, and phi minus what? Phi minus, here we have to have electron quasi Fermi potential. The difference between electrostatic potential and electron quasi-Fermi potential is required here, and that was kBT over Q. That was the one we had to have. So, are you with me? And that was the one, our conventional notation. After that, what we did was, okay, instead of our conventional notation for this electrostatic potential, we just introduced something like this: phi minus certain reference value and also reference value. Of course, this reference value was the potential at deep substrate, you know, and here we have here electron quasi-Fermi potential. So now this guy is now called as once again electrostatic potential, and this another one, and I exponential phi reference divided by summer voltage. Yes, this quantity is corresponding to what? Corresponding to the electron density at deep substrate, and we had potential kBT over Q, and eventually we have here minus phi n kBT over Q. The reason why I repeat this job again is, up to now we have used only terms, the first two terms. Yes, so in our MOS capacitor study, we say that, okay, if we adopt Professor Tower's potential convention, then electron density is given as the minority electron density times exponential phi over summer voltage. That was it. But what was missing? The missing part was this guy. Why we were able to omit this part, this exponential part? There was an assumption. The assumption was, yes, quasi-Fermi potential is equal to 0 volt. This is because we have just applied 0 voltage to our entire substrate. So inside our substrate, quasi-Fermi potential for electrons and quasi-Fermi potential for hole, both of them are entirely 0. That was the justification for our system. Let me just draw once again. The situation like this: here we have a silicon substrate, and here we have oxide, and here we have a gate, and now we have grounded substrate. So that's the reason why this ground just provide us phi n equal to phi p equal to 0 entire over our silicon substrate. Of course, here we have gate voltage applied to the metal part. However, that quasi-Fermi potential is not affecting this silicon substrate, because we have very effective and perfect insulator called as oxide. So impact of this gate voltage is fully prevented by this oxide. So this silicon region is entirely dictated by this ground. So that's the reason why we were able to safely say that potential, quasi-Fermi potential, is 0 for our silicon substrate. Now let's come back to our current situation. If I draw once again this system, this is really interesting. So now if we have a look at this system once again, now you can find that there is no longer existing only one single contact effective. Here we have a substrate contact. This is still grounded. Yes. And here we have a source contact. Yes, this source contact is still grounded. And now you know that here we have a drain. This is not in general, not grounded. Then can you understand the difference? Previously, although there exists a metal gate, but metal gate was separated from silicon bulk by this very good oxide. But now this drain, which is biased to non-zero voltage, is directly attached to the silicon bulk. Actually, it is a part of a silicon bulk. So if I ask you a question like this, at a certain arbitrary position, what is the electron quadriformy potential, and what is the whole quadriform potential? If I ask you this question, then maybe it is really difficult to answer that question, because now there are two contradictory conditions. One guy, or there are three guys, but they are in the same part. So these two guys say that, okay, quadriform potential should be 0 volt. And this drain says that, no. We need to set quadriform potentials to, for example, 1 volt instead of 0. They are competing. So what we can expect is, if we approach it to maybe this reason, maybe quadriform potentials would be quite close to 0 volt, because these two guys agree that 0 volt. But if we go to this junction part, then maybe there will be certain conflict. M plus drain wanted to keep the quadriform potential quite close to its own applied bias, drain voltage, and also substrate want to keep them as 0. So that is the point. So are you with me? So why we are talking about this quadriform potential again and again? It is because in our expression, all over our electrostatic potential, all over our electron density and hole density exponentially dependent on quadriform potentials. So therefore, selection of quadriform potential is extremely important. But previously, when we consider MOS system, there was no difficulty. Just globally set them as 0. That was okay. But now, since we are working with MOS transistor, which can be biased non-zero voltage, so we have to select them. That is the main reason why we need this consideration. And the answer is quite easy, once again, quite easy to answer. Please think about your PN junction, which is biased in non-zero bias condition, forward or backward. Maybe you have studied the behavior of your quadriform potential. How does it look like? Where do you have the change of each quadriform potentials? When you have a PN junction, your whole quadriform potential is almost constant all over your p-type region, and even for depletion region, only in minority n-type region your whole quadriform potential changes. On the other hand, if you consider electron quadriform potential, inside the n-type region, depletion region, there is no change in your quasi-forming potential. Only inside the p-type region, quasi-forming potential changes. So if you don't understand my previous statement, then please revisit your previous course for p-n junction at non-zero bias case, non-equilibrium case. Then you will find that certain graphs shows splitting of your quasi-Fermi potentials. Okay, so this is a depletion layer, and you will find such kind of diagram. So please revisit. So when we consider this kind of previous study, what we can say is we have no idea about what happens here and there. This is out of our interest. We are currently interested with this region underneath the gate part. So this is entirely p-type doped. So now what we can expect is, at least in terms of our whole quasi-Fermi potential, so this one is solely determined as 0 volt. How can you say so? Although here we have, let me just say, although here we have a source and drain, and also drain wanted to make the potential, quasi-Fermi potential, to its drain voltage. However, this is n-type. So in the case of n-type, all kinds of change in our quasi-Fermi potential, whole quasi-Fermi potential occurs in this n-type region. So this one cannot make any impact on this whole quasi-Fermi potential. But let me just come back to the other one. More complicated one is, how about electron quasi-Fermi potential? Actually, if we yes, here it is not that certain what happens to this position and that position, another position. What we can certainly say is, at this point it will be 0, and at this point it will be VD. But in between any point, can you find a certain value? It is a little bit difficult to say. So what we do is, okay, we allow it varies. So say that now we can say it can be a function of a position x and y. We have no idea. Let's call it as an unknown variable. So we wanted to solve this phi sub n together. Then up to now we have to consider electrostatic potential as a function of a position and y. So that was our original Poisson equation, 2D Poisson equation. And after that, what we did was, by adopting gradual channel approximation, so we were able to just treat y variable as a parameter. So instead of solving complete two-dimensional Poisson equation, we were able just to solve a set of one-dimensional Poisson equation along x direction for several y values. That was our achievement. However, inside this 1D Poisson equation, we once again get this unknown variable called as electron quasi-Fermi potential, and in general it is also position dependent quantity. That is the story up to now. So are you with me? So please try to understand the situation. This is so much systematic derivation, so if you miss some part And if you understand miss one step, then maybe you will be lost. So if you don't understand this derivation procedure, then please let me know. So yes, so although we have no idea what the electron quadriform potential itself looks like, we have no idea, but we will say that okay, it is given. Then now what we can say is this electron density is simply given as this previous form n exponential minus phi n kBt over q. Wow, we can do it. And this is still treated in x and y in general. Up to now, this is the situation up to now. But here we make great simplification in this slide. So electron quadriform potential, so electron quadriform potential is in general regarded as 2D quantity, but here, sorry about the notation. So sometimes I use V. In this slide, I use V in order to make it clear, because you know, when I say this one, maybe sometimes students are confused with just electrostatic potential. So here I intentionally write down this V. So anyway, in general, it should be written as x, a function of x and y. So once again, x is vertical direction, and this is lateral direction, channel direction. But now we say that although it is a function of position, general position, but we will say that this is only a function of lateral position, not vertical position. So simply speaking, I'm saying that for this slab, they share the same electron quadriform potential, and also for this guy, they share the same electrostatic potential. For example, let's say they happen to be this one is 0.1 volt. It's okay. And happen to be this one is 0.3. It's okay. But in its approximation, we don't allow, for example, this point is 0.35. It is not allowed. Along vertical direction, we have no changes, no variations in electron quadriform potential. How can we allow this kind of approximation? If we allow so this quantity variation of our quadriform potential with respect to the vertical direction, if this is not 0, then there will be the current conduction along vertical direction. That is quite obvious consideration. For example, as I told you before, let's say that this is 0.3 and happen to be, let's say that this is 0.1 volt. If we have two different quadriform potentials along these 2 points, then okay, there will be current conduction along this vertical direction. So can you imagine the current conduction in vertical flow? So here we apply 0 volt, and here we apply, for example, 1 volt, and current is flow in this vertical direction. Can you understand, or can you allow this kind of a current conduction? So actually not. At this slab wise, there should be no current conduction. Current should flow in this direction. That's the point. So if we neglect x directional component of our current, electron current, it means that also x directional component of gradient of electron quadriform potential should vanish. Otherwise, we will have a current conduction. That means that although we have, in general, we have to have x dependency and y dependency, but x dependency can be safely gone. So we have only position channel dependent electron quadriform potential. This is really important. So now, by adopting the gradual channel approximation and also this slab-wise electron quadriform potential, what we can do is, for each slab of our transistor, what we can say is, we can just solve this 1D Poisson equation. It is enough to consider our system. Also, inside our slab, quadriform potential is a constant. This is great simplification. Now we can treat inside this slab, we can treat the electrostatic electron quadriform potential as a given number, so that introduce only really minor change in our previous expression. Compared with the previous expression for our electron density, the only difference is now adoption of this minus V factor, because this one can be a position of channel direction. But please note that in our treatment, y is not an independent variable. Y is just a parameter. So at a given, in order to specify a given cross section or slab at a given position y, then we can solve this one-dimensional Poisson equation. Then the remaining procedure is amazingly simple, because just do it once again with your own exercise. So when you do it once again, the only difference comes from the expression for electron density, and also that introduced a small modification in only electron density. When you have a look at the expression for square of electric field, square of electric field can be written as this form, and you may find this red colored one. This red colored one is effective only for these two terms, and this two term is originated from electron related one. All other parts are not related to the electrons. For example, this guy is clearly related with holes, so you can find that holes are not affected by this modification, and also Na, that is not modified by this modification. So that's the reason why these guys are not changed. Only the one related with electron density is modified with this exponential factor, and please note that this is once again only a y dependent one, not x dependent one. So for given slab, you can say this v is a given constant, given number. Okay, so yes, so that's it for our expression. So please understand, this simplification was not obtained by from error. We have introduced some approximations, but valid approximations. The most important one was gradual channel approximation. So neglecting the second derivative of our electrostatic potential along channel direction. So therefore, we were able to get just 1D Poisson equation. And in this 1D Poisson equation, we have to consider hole density, electron density, and Na, integrate them. But hole density is not affected because hole density is governed by just substrate voltage. But electron density, that can be also affected by drain and substrate source. It is obtained by compromise between them, among them. So 3 different source, drain, and substrate. Each part try to make some influence on quasi-Fermi potential for electrons. So we introduce unknown variables. In general, it can be a function of a position x and y, but x dependency was neglected from the observation of x directional, vertical directional current conduction should be 0. We need only non-zero current conduction along y direction. Okay, we can say that this is allowed. However, if we have vertical direction, then that should be 0. From this consideration, we can have this simplified form. So then let me just summarize. What we have done is, although we have introduced some reasonable approximations, the result is quite simple. We can treat each slab of our MOS transistor as just MOS transistor. MOS capacitor, whose electron quasi-Fermi potential is modified by amount of V sub y. That's it. Previously, when we consider surface inversion, the condition was band bending should be 2 times phi b. But now we have different numbers here. It is because this is the reference potential, reference quasi-Fermi potential. So you can understand this one. So simply speaking, if we go to source part at source end, we assume that V y equal to 0 is 0 because this is grounded. So in this case, our surface inversion condition is the same with that of MOS capacitor. However, please think about the other way around. The drain end. In this case, your position y equal to L. In this case, electrostatic potential is not 0, but it is written as a drain voltage. Then in order to make surface inversion condition, then you need higher band bending. So you have to understand this points. So you can see that also this part is added to estimate maximum depletion layer width. So, but please note that here we have two different expressions, and this is surface inversion expression. Although it is just a theoretical kind of artifact, but it is exact one. We can define surface inversion in this system, and maximum depletion width is not actually. We can even wider depletion width because surface potential can be even slightly increased even beyond inversion onset of strong inversion. But please treat it as just a rough estimation about maximum depletion width. Anyway, so I think that I have prepared more materials, but I have to stop here. This is a summary. With the gradual channel approximation, our MOS expressions can be readily reused only with modification by V. This is electron quasi-Fermi potential, and this is slab-wise. So at every slab, you must recalculate this quantity. So are you with me? So let me just give you one example. Say that here we have 1 micrometer long sample. Wow, this is really long. And here we have V equal to 0. And let's say that we have applied a really small voltage, like V equal to 1 millivolt in this case, just 1 millivolt. And now we have we assume just linear variation of electron quasi-Fermi potential. It means that if we go to certain position, for example, let's say that if we go to y equal to just 0.5 micrometer, then we assume that electron quasi-Fermi potential is also 0.5 millivolt. Then now please try to estimate those numbers. For example, in this case, what is your surface potential? How can you get your surface potential? You did it as your homework. Just to draw the general expression between quasi-Fermi potential and general expression for your charges and surface potential. Then from that number you can find, at least theoretically, you can calculate the surface potential. What I want to ask you is, in the same situation, can you calculate the surface potential at this point? The only difference is your quasi-Fermi potential is not exactly 0 but 1 millivolt. How can you do that? You can solve once again MOS equation with this modified expression for your surface charge, and even for any arbitrary position, for example 0.5 micrometer, now you have a different electron quasi-Fermi potential, and also you can solve that problem. So are you with me? So in general, although we have to solve 2D Poisson equation, but by understanding and adopting these approximations, now we were able to get a set of 1D equations. We have tons of equations. How many equations are there? So it depends. if you introduce 100 slabs in your discretization, then you will have 100. Analytically, you will have infinite number of slabs. For example, this y is not in general discrete quantity, but this is just a coordinate, so you can define any arbitrary y values, but in reality usually we introduce a certain y values, for example 0, 0.1, 0.2, blah blah blah. So then for those cross sections you can solve this 1D equation and get the surface potential. So maybe solving just one equation was quite heavy to you, but now it means that we have to solve this equation many times. So, well, in analytic sense it's not that easy, but anyway, by using computer programs, so we can do it. So anyway, this is the end of our today's story, but this is not the end. Our journey to the power saw double integral is not over yet, so let's keep our discussion in one day. Thank you.